We take a look at Module 10.2 now, and in this module here, we're going to cover a couple different things. We're going to take a look at some control algorithms, control system analysis, controlling first-order plants, and then talk a little bit about second-order plants and our plan for controlling them as well. So as this relates back to our textbook, we can take a look at sections 10.4, 10.5, 10.6, and 10.7. Where 10.4, we're looking at this PID control algorithm. 10.5 is going to be the control system analysis section. 10.6 is going to be for first order, and then 10.7 is going to talk about our second order plants. Now, a lot of the lecture today is going to be spent going over some practical applications relating back to our control and our feedback of different systems. So the first topic we're going to talk about within this section is our PID control algorithm. So within this, the control element is designed to act on our error signal in order to produce our control signal. So the logic that's used for this purpose is known by a couple different terms. It could be called the control law, the control action, or referred to as the control algorithm. Now, if we see a non-zero error signal result, this could be from two different things here. It could either be from a change in command or from a disturbance. We've talked a little bit about disturbance in the previous section. So as we're talking about our controller, one of the main functions of our controller is to keep this controlled variable near its desired value when these disturbances or changes in commands occur. So some more specific examples here of some of the control objectives are the following here. 1, to minimize the steady state error. 2, to minimize our settling time. And 3rd, to achieve the other transient specifications, such as minimizing the overshoot. So we're going to take a look at some of the key terms and phrases we're going to utilize within this module. The first term we're going to take a look at here is two-position control. Now this exists when we have two possible values, and the output, our control output, is taking on one of these two values. Now a common time that we see this is within home thermometers. So in a home thermometer, whether it's a digital or an analog one, you can set it to a threshold temperature. And when it reaches that temperature, it's either going to turn on or turn off. So those are the two values of on or off that it could be, and it can only take on one of those at a time. So that's an example here of a two-position control. The next control term we're going to take a look at here is proportional control, and where this occurs is when the control signal is going to be proportional to the error. Next, we'll look at this integral control action. Now, where we see this is sometimes the proportional control results in the system reaching an equilibrium in which the control system no longer changes. So if it no longer changes, what that means is this is going to be allowing a constant error to exist. Now, for this case here, if the controller is modified to produce an increasing signal, as long as the error is 0, the error might be eliminated. Next, we'll take a look at a derivative control action. Now, what this is an action that produces a control signal even if the error has completely vanished. And what this does, this tends to cause oscillations within the system. And it suggests that the controller should be made aware that this error is approaching 0. And there's different ways in which we can see that this error is approaching 0. And this is the basis of our derivative control action. Last, what we're going to take a look at here for our terms is PID action. Now, PID action occurs when the integral and derivative action are used with proportional action. We obtain a proportional plus integral plus derivative control algorithm, which is why we abbreviate this as a PID. We're going to talk briefly now about a control system analysis. So this approach to selecting an appropriate control algorithm and computing its values. So central to this process is the understanding of the system's transient and its steady state behavior. Now this is especially true when we're talking about the effect of the command and disturbance inputs on our error function. So how do we take these disturbance inputs into effect? How do we calculate those? Is all part of this process of the control system analysis. Now, if we're talking about our error within our control system here, this, as we recall, is the difference between our R of t, or our command input, and our control variable C of t here. So this is our E of t, our error of the control system, given by this relationship here. And what we can see is all of these within this relationship here are going to be a function of time. And we can utilize the fact that this is dependent upon time and a function of time if we're looking for specific things within it here, potentially a peak error or a settling time error and things like that. We can go back and use the fact that this is a function of time in order to calculate and find those. Now, if we're looking at the error within a system that has some command input and some disturbance input, this error is going to then be the sum of the errors caused by the command and the disturbance. Now, these errors are called command errors and disturbance errors, depending on which one we're referring to. So graphically, we can look at those two and see the difference here. So if we're talking about our command errors, here's our steady state command error up top here. So we can see the difference between here. There's our R value coming across here at time t1 from our graph there. So this is our command error there. Whereas we can see from this down below here, this is what we're referring to now, this distance in between these two, as our disturbance error. Now, a great resource we have in our textbook that I just want to briefly mention here is table 10.5.1. So this is our final value theorems. So for the different cases here, either our general case, our step inputs, and our ramp inputs, it gives us a relationship for our steady state value, or C sub SS here. So we can go through each of those cases and get this general relationship for each of these if we need to reference back for either of these cases, general case, step inputs, or our ramp inputs. So as we're talking about our different types of inputs here, step inputs aren't the only type of inputs we want to utilize or even talk about when we're talking about our systems here. So another very important function here, very important input, is our ramp input here. So typically where you see a lot of these is in motor control type of things, where you don't want to just all of a sudden turn it on and go full blast at the highest speed or the desired speed of your motor. You want to slowly ramp up to that desired speed, keep it at that, and when you're done, you don't want to just shut it off and stop it dead either. You want to ramp back down. And the amount of time it takes to get from an initial velocity or a stop point where it's 0 velocity up to your desired velocity here, you can set that amount of time there. So how quickly it ramps up to your desired speed here, how long it stays at that speed, and how quickly it ramps back down and shuts off. So that's a great method here where we can utilize a ramp input for a practical application. Now, this also is a great test of the control system's ability to follow a constantly changing command. So it may not just be, okay, I want to ramp up and stay at a constant speed, shut off, we're done. It may need to ramp up to a certain speed, stay there for a while, ramp down to another speed, stay there, constantly changing. And how quickly it can do that is going to be, again, a great test of the control system's ability to follow these commands, change it, how quickly, how accurate is it. So let's take some of this and tie it into a design of our system here. So if we're talking about designing a control system, we may be typically given a lot of the information of what we need to use within that system. So a lot of times the plant is actually going to be given. This is something that might not be able to be changed. So as an engineer, again, you might be given a model of the plant and the actuator, and then from that, you're going to need to design your control system around that. Or there may be times when you're expected to develop a model for the plant or the actuator based around other given information. So what they specify in the project, whether it's something a research project where you have to utilize certain things and design the system around that, or if it's a job application where they've already bought some of the parts of the system and you need to figure out how they all go together and design the system to fit all those in, this is something that would be part of this whole design process within the control system. So in a lot of cases, your physical type of your controller, whether it's electric, pneumatic, hydraulic, digital, whatever it may be, and the actuator type as well, is again going to be specified for you. So they give you that information. Okay, you're going to use a controller that's going to be an electronic controller, and the actuator is going to be a pneumatic actuator. So therefore, you need to design a system based around that. Now that's a typical case, but there are going to be other cases where as an engineer, you're going to have to choose which of those you do. And a lot of times this choice will almost be made for you based upon the application of what you're doing. So if you know the system needs to perform a certain way or do a certain task, it's going to eliminate some of these different options for you, and it'll kind of specify within that down selection process which one you're going to utilize for the specific system. So as we're talking about all this design criteria here, this is going to tie into some of the later courses that you guys are going to be doing within your ME curriculum here. So ME 171, we're going to get into a lot of the information on how you select some of these controllers, some of these actuators. And this could be things that include cost, weight, performance. All of these things come into play, and you need to compare them all together and decide, okay, if this is the minimum amount of performance and I can't exceed this budget and I can't exceed this weight, how do I down select all of my different options for my controllers and actuators and everything else within the system in order to fit that in and still get the best performance while maintaining all the other minimum criteria that's specified by the company or by the research project. Now, another big thing when we're talking about actually designing systems here is the command and the disturbance inputs. Now, sometimes these might be specified, and a lot of times the command input might be specified to you, and most times your disturbance inputs aren't going to be known. It could be a random thing, it could be jitter, it could be noise, it could be background within the room of the test system, all kinds of things can be your disturbance input. So it's your job as an engineer to develop some type of tests in order to work on your system and optimize your system based upon this. So you can set your step frequencies, ramps, trapezoidal, or sinusoidal inputs for your command input for this here. And what you can do is utilize that information in order to back out what is the disturbances. Because again, your disturbances might not be known. These are random, and you need to calculate and figure out what those are. So one thing that we really do want to look at as we're doing these testing, setting up and trying to determine our disturbance inputs is the design specification. So again, something given to you by the company, the research project, the problem you're working on, there's going to be specifications within that. And a lot of times the specification is going to help make it clear what you could utilize as some of your inputs here. Should it be a ramp input? Just slowly step up to a certain speed, stay there and go down. Should it be a sinusoidal? Is it a cyclic loading type of problem? So a lot of stuff within that design specification is going to help make it easy on what you're going to utilize for an input. So that does provide you a lot to think about and makes you realize that there's a lot of different options and a lot of different considerations that go in when doing control system design. So one thing that's really nice to have is a generalized procedure that you can follow, things to ask yourself, steps to go through as you're doing the control system design. So again, a lot of this is going to be based on a couple things. It's going to be based on the system model and the performance specifications, whether these are something you developed yourself or these were given to you as a set standard. What you can do with those is from there, you can choose a control action and obtain an output, an error, and actuator equations based upon your system model and your performance specifications. So the next step in our procedure here is going to be to analyze the system for stability. Is it stable? So if it cannot made to be stable, then we need to take a step backwards and try to figure out, okay, how do we make this stable? We're going to stop and try a different control action from there in order to figure out how we can make it stable. Now, if we determine that it can be made stable, from there, what we need to do is figure out the constraints on the control gains in order to achieve the stability for the system. So the next step within this here is we want to be able to evaluate our steady state response. So in order to do this, we're going to use the given command and disturbance input functions here, whether it's a step, a ramp, whatever it may be, sinusoidal from there, in order to evaluate that steady state response. Now, typically we can do this utilizing the final value theorem. So this is where we're going to put a practical application to that final value theorem that we've been looking at earlier. And within this, we're also going to determine the constraints on the gains in order to satisfy the steady state specifications within the system. Last, what we want to do is evaluate the performance of the system. So evaluate the transient performance based upon the transient specification. So a lot of times these specifications are going to be stated in terms of a desired dominant time constraint or in damping ratio. So based upon that, we want to be able to go back and evaluate the performance of the system. So we talked within this procedure about determining the stability of the model. So this is a great chart to reference back here. It's a quick way to determine the model stability without the need of solving for roots of the equation. So we've seen in a lot of the example problems we've done, this can be rather long and involved. If there's a shortcut, quick check that we can do, that's a great thing. So this is going to be a very useful resource for us in order to get these results right here within this model here. So we can go through, we can see we have our model function, our transfer function, characteristic equations, characteristic roots, our damping ratio, our time constant, our maximum percent overshoot, complex root pairs, and our damping value down here, how it corresponds to the root pair. So all this information is quick and dirty, some great equations and calculations that we can quickly reference back to in order to determine the stability of the model without going again through and solving for the roots. Primarily, we've been talking about first order plants. So what I want to do now is take a minute here to talk about controlling second order plants. And I think the best way in order to do this is to take a look at the general form of a second order plant. If we do that here, we can see we have our equation of motion for a second order plant given to us down below here, where the equation of motion is given to us by our I theta double dot plus c theta dot plus c theta is equal to t of t minus td of t, where our I is going to be our inertia. Our C term here is going to be our damping, and our angular position is going to be our theta term here. And we can see now that our T is our actuator torque, and our disturbance torque is given to us by T sub D. Now from this, we can see here that our plant transfer function is given by the relationship here of our 1 over IS squared plus CS plus K. And if the plant is stable, then our I, our C, and our K are all going to have the same sign. So that's a great way to check our stability of our plant right there.